Perfect. So yeah, as Amadi said, this is going to be kind of in two parts as well. So I'm going to do the first section where we're going to look at GNSS data, as it comes out of the receiver, essentially, and how we can use that to get an ionospheric signal, essentially. And that's really important because there are a lot of problems. Right? GNSS data is great. Right? I use probably more GNSS data, or my models do, than anyone else in the world. Um, and so it's really great as a measurement because it's cheap, it's everywhere. If you want to study small scale things, large scale things, there's a lot you can do with it. But it is not designed as an ionospheric measurement. And so to get the ionospheric data out of it, you have to do a lot of work. Um, it's not too bad, and we're going to go through that today as how you actually get that signal out. But it's not designed for this. And that's important to remember. So when you want to understand, whenever we're doing anything with data, you need to understand at least a certain amount of how the data works, where it came from, so that if you see something strange in it, you can know, is this something interesting that the ionosphere is doing, or does this look more like a problem with the data? And so that's sort of why I've structured this first part how it is. So we're going to be really low level of just understanding where a TEC measurement from GNSS comes from. Um, so that later on, we can know things. And also, as you go forward, you might have, depending on where you are, access to a bunch of GNSS receivers through either your nation's geodetic services that are quite common. Um, oftentimes there's tech data that, I don't get access to because I'm not in a certain country. But those ones won't be in the big databases, right? They won't be just a tech product you can necessarily download. So it's good to know these skills and have some code that can help you so that you can use your own instruments. So again, we'll talk about some fundamentals of it and how we read this data and how we calculate tech. And then Mahith will take over and show you some other things of like using VTech from Madrigal, I think, and then some scintillation stuff, which should be interesting. So, what is GNSS? So, it stands for Global Navigation Satellite Systems. And for a long time, people just used the term GPS because that's all that there was. But now we have a lot of systems like this. There's GPS and Galileo, there's GLONASS, and there's BeiDou. There are also regional systems that you might see. So QZSS from Japan and IRNSS for India. They're regional systems because the way that the orbits are set up, they're either geostationary or different kinds of orbits. So they're designed to augment signals in specifically those regions. But right, as I kind of say in the name, they are for navigation, right? They are for positioning, navigation, and timing. So they're for figuring out where you are, in Earth or near Earth space, for figuring out how to get to where you're going. So, you know, mostly like Uber and food delivery these days. Um, and also timing. So, for example, in some of the research our group does when we're building radar systems, we need to be able to network the radars together. They need to know what time it is very precisely. And GNSS is very good at that because all it is a timing signal. You take some atomic clocks and you put them in satellites, you put those satellites in orbit, and you just broadcast. It is currently this time. And that is essentially all that these satellites do. They just broadcast what time it is. And so you can determine where you are based on this timing signal, right? So if you know what time it is, and the satellite knows what time it is, and it tells you it is currently whatever time, then that signal takes a certain amount of time to get to you. And if you have multiple satellites, you figure out how far away from you all of those satellites are. And if you know where the satellites are, then you know where you are. And that's, in a nutshell, how GNSS works. So in practice, it's a little bit more complicated, right? So they're broadcasting several different kinds of information. So there's this ranging code, which is a pseudo-random code that has that time signal encoded in it. It also broadcasts some things like the satellite clock corrections. The clocks drift over time, so the satellites say, "Oh, by the way, my clock is wrong by this much." They broadcast the satellite ephemerides. I never know how to pronounce that word. Um, so that is essentially the satellite tells you where it is, right? It gives you an orbit for where the satellite is, and then some other information like a rough ionospheric correction. So all of these things are sort of encoded on the same signal. You can build a nice little antenna and you can receive these signals, and that tells you where the satellite is, what some of the errors are, and how far away the satellite is for all of the satellites. So you can do the position and navigation and timing. And these can be set up to, right, you can record, right? So really in how it's supposed to be used. You have a GPS in your phone or something. Your phone doesn't record any of this information because it doesn't really care. It just wants to know where it is. But we can record this information, and so this is recorded usually in RINEX format, which is essentially everything that the GNSS system observed, and you can just record it all down. So this includes observation data, but we can also record these satellite positions and things like that. So one thing that's important to know is, again, it's not just a single ranging code. So, for example, GPS uses three different carrier frequencies, which will be really important for us, right? If it only used one frequency, we would not be able to do anything. Um, so we have you know, L1, L2, L5 in the case of GPS. They're all at slightly different frequencies. And then they have different codes on them. So you have the C code and the P code are sort of the classic ones. Then there's a whole bunch of new ones that have been invented more recently. But um, what's really important, the C was the civilian code, the P are the encrypted military codes. The P codes are more precise. Um, but we don't need to dwell on this too long. But there's some interesting history there with, sort of Cold War tensions and things like that. Um, so what's important to know from all of that is we have ranging codes, right? We have these codes that are encrypted on the signal, and they tell us essentially what time that signal was broadcast. Um, so the other part of that is knowing where the signal was broadcast from. So these are the RINEX navigation files, which is what we'll work with in this because there's some nice code for reading it. But there are other ways to know where a satellite are. So there's something called an SP3 file, which is produced much later after the fact. It takes a few days for them to be made, but they're very, very precise. If you need to know exactly where a satellite is, they're very good, but they're, I think, only for GPS and maybe GLONASS. You can use two-line element data, which are what people use for doing orbital prediction. So if you are trying to keep satellites from colliding with each other, TLEs are what people use for that, but they have them for all satellites, so you can use that to get navigation satellite positions too. These all have different levels of precision, but for tech calculations, they're all good enough. But in our thing, we'll work with the navigation files. This is what a navigation RINEX file looks like. It is a massive pile of numbers. You don't need to worry about that. But um, the nice thing about them is every satellite broadcasts information about every other satellite. So, all of the receivers around the world get the same information. So you don't need to get the specific navigation file that your receiver got. You can just download one of these global files, right? So here's a link to CEDAR. You do need to make an account for that, but here's another place where you can get navigation files for any receiver. They'll all work fine. They're not going to be identical, but the information in them will be identical. But this is where you find out where the satellites are, which is important if you want to, say, do a tech calculation. You need to know where your receiver is. You need to know where the satellite is. All right. So that was just a bit of background, but we'll really worry about sort of tech stuff now. So This ranging code is essentially just a bunch of random zeros and ones, you can think of it, right? And what the receiver does is it tries to find a maximum, it knows what those random codes should look like, and it's receiving a random code. So it is trying to correlate its own random codes with the ones that it's receiving. With the idea being this gives us the time delay from the satellite to the receiver. So that correlation, it will peak at whatever the true value is, but it's also quite noisy. But essentially, right, you get this thing which is based on the speed of light and the time at transmission and the time of the receiver, ideally. But there are other errors that we'll see. But essentially, that's all it's doing, right? It's very easy. The problem is it's very noisy. The correlation isn't perfect, and then sometimes the signal will reflect off of nearby objects. And so this gives you something called a multipath error, where it will now correlate differently because you essentially get two or more peaks in this correlation signal, which gives you these very strange errors. And these get worse the closer you are to the horizon, generally. So this is a big problem for scintillation studies, but it's also a big problem just for finding out what the tech is. So if you hear people or read a paper and it talks about like cutting off low elevations, this is why. It's to get rid of multipath errors. Phase is another thing that we can keep track of. So we have this carrier signal and we can keep track of how much, how many cycles we've seen essentially. And it gives a measure of relative distance, right? So you can see here, this is just on the left-hand column, these are pseudo range. This is the ranging code, right? And for different carriers, this is the first carrier frequency, L1, this is L2. On this side, these are the phase ones, L1 and L2 on the right-hand column. And you can see they look basically identical. Now, if you take a difference between them, you can see the codes are very noisy and the phases are very smooth, but have these sort of weird jumps in them. This will come up later. So phase is nice because it's very smooth, right? You don't get nearly the same amount of multipath error. They generally have a lot less errors. It's you don't have this correlation problem. It's very nice and smooth. The problem is that it's completely arbitrary, right? You could be off by millions of kilometers equivalent, or millions of ionospheres, and it has no idea. It's just an arbitrary number. It's not an exact measurement or not a precise measurement. But what we're trying to do with tech processing, and we'll see, is essentially trying to combine these two. So you have one that is accurate but noisy. You have another one that is precise but arbitrary, and you want to combine them together to produce a better signal. So, this is what a RINEX observation file looks like, a version 2 file. So the pseudo range and the phase that the receiver records gets stored in the RINEX file. Some of them will also record some other stuff like signal strength and Doppler shift. So signal strength is used to calculate scintillation. Doppler shift, as far as I know, no one in the ionospheric community really uses it for anything, but presumably maybe we could. But this is it. This is essentially all you get from GNSS. You get your pseudo range, your phase, and maybe signal strength, maybe Doppler shift. And then this is it. Everything that we do comes from that. So when you are downloading and looking at RINEX data, there are a lot of confusing things. So there are different formats. RINEX version 2 used to be, for decades was what everyone used. It's becoming less and less common because it's really only supports GPS and to a lesser extent GLONASS, but it really is not designed for all the constellations we have today. It often uses these short file names, which we'll talk about. Then there's RINEX v3, which is becoming more and more common. It tends to have these sort of longer, more descriptive file names. And I have links in here. I'll send out the slides to everyone so that you can have links to the format descriptions. But the software we're using to read them can read all of them just fine. RINEX v4 has also come out. It doesn't really change the observation files. It's a change to the navigation files. Um, the code we have cannot read RINEX version 4 navigation files, but it can read RINEX version 4 observation files. So, um, so the short names are very simple. The first four characters is the station ID. The next three characters are the day of the year. The last digit is telling you something about whether it's a daily file or an hourly file. Um, then you have here in the file two-digit year. So for this year, it'd be 26 for 2026. And then the file type is O for observation file, D for a certain kind of compressed file, N for navigation, etc. The reason that they're this size is that they date back to an era when most computers could only have 10 character file names, believe it or not. So you could not have a file name longer than 10 characters. So this is the file name they used. It was the most information you could pack into what computers of the time could support. Um, so, just some examples, right? Here are some files, right? So what can we know about this first file here? If anyone wants to pipe up. What's the station name or the station code? Ah, you're all just like my students in my normal classes. Um, yeah, exactly. Okay, there we go. All right. Yeah, LLAG. Now, unfortunately, we have no idea where that is, unless you happen to know um, what it is. But yeah, so it is what, right? It is from 2016. It's an observation file, right? Because it has the O. It's a daily file because it has the zero here, and it's from day of year 123, right? Which is easy enough. And it's not compressed. Uh, the next one is BRDC 181, right? So this is a navigation file of from 2022, the 181st day. It has, it's compressed. And it's BRDC, which actually isn't a station. This is one of the global navigation files. So uh, this is just a synthetic file that, excuse me, has been created by the IGS to have all the daily innovate data. This next one is from, you know, uh, in this case, I happen to know where this is from, right? This is from Inuvik. So the station code actually kind of has the name of the place in it. And it is a 15-minute file that is starting at the half hour, right? So it's in the second hour, it's got to be, it's half an hour into that, it's a 15-minute file, but, right? So we can know some things about it, but it's not nearly as informative. Um, but when you're scrolling through, a whole bunch of these files, it's helpful to at least have some information. So the long file names are much more helpful. They have much more information. So you can see here, right? These are the same files from before, but with the long file name. So you can see LLAG. Then it has this second set of characters don't often get used very much. It has, right, ESP. So this is from Spain, Hispania, right? It says R, which is, if I remember, means it's a mixed file. So it has multiple constellations in it. I don't entirely remember what that one means, right? It's 2016, day 123. It starts at 0 o'clock, right? It runs for one day. It has 30-second data in it, and it is a mixed observation file, right? Much more informative. You know. Here you can see, right, BRDC, instead of a country code, it says IGS, so now you know it's one of those synthetic global files that doesn't really exist. Um, it runs for a whole day. Here, right, Inuvik in Canada, right, it has the start time in it. You don't need to decode that other thing. It lasts for 1 hour. It has 1 second data in it, right? So it's a higher rate file. It has much more data than the other ones. So the long file names are much more useful, and this is why everyone's switching to them. V3 files are almost always in the long file name. V2 files almost always use the short file name. Um, but that's not always the case. Um, this is one thing you will learn is that no one knows what they're doing generally. Or everyone has their own unique way of doing things, we'll say. So you will find long file names with V2 data. You'll find short file names with V3 data. It's all a mess. You can't assume the data type from the file name, but it's generally right. Um, just makes everything fun and spicy. So, all right, we'll go to our first activity. So, I hope I think most of you were around at the beginning when we were trying out getting the Git repository to work. Um, chat go. Did I close the chat? Sorry, Amadi, I think someone needs help entering the the room.
Yeah, I'm taking care of that.
Okay, thank you. Perfect. So has everyone downloaded the Git repository that I put a link to at the start of the chat? Or maybe has anyone not been able to do it yet? Okay. And again, sure. So here is so that is the link to the repo. If you make a new folder and go into it with Python, right? Um, right, you can install it with pip. No, why is it not letting me copy and paste my own? I'm not allowed to copy and paste things from here. You should be able to do that. And then, yeah. So, Anjali, what error are you getting? Yeah, if you can't do it that way, you can always, right, you can just click here and download as a zip file, right? And then you can open that up. Oh, does that not work? Yeah, just do the zip way then. That's me. That's me being lazy. So I didn't set it up as a proper project. I just assumed that I'd be able to do the git install thing. But yeah, that's me being dumb. Just download it as a zip file. Uh, yeah. Yeah. Okay. Now that I have not given everyone impossible instructions, Hopefully everyone will be able to do it. So if you do get it working, you should get something that looks like this. Um, right. So the first one to open will be setup.py. It gives the instructions on how to make a new virtual environment and get everything working for VS Code. Um, but it should hopefully work for everyone. Um, yeah, the only problem is I think depending on what Jupyter notebook software you're using, this line. So someone brought it up actually in the Ionosphere lecture I did, that GeoRINEX is really slow. And you're right, GeoRINEX is really slow, which is why I made a faster branch of it. I've just forgotten to actually merge it back into the main GeoRINEX package, and I probably should do that at some point. So if you install my version of GeoRINEX, it's very nice and fast. Um, but if you just run this Jupyter notebook, it should install all of the libraries for you. So that is there working. There is this assignment one, which is sort of what we'll work through. Um, so there's a folder here called data, which has some example RINEX files that we'll use in it. Um, in the meantime, there's lots of places where you can find data. So I have links to this again in the PDF that I'll send around. Um, but for example, this is Garner is a big archive of them. You can see they have loads and loads and loads and loads and loads of GNSS of RINEX files, right? So if you want to do some tech studies, now most of these are in the US. There's some global ones and then a lot of them in and around the US. Right? But there is an incredible amount of data here. This is just for a single day, right? All of these are different stations. They're basically all in the US. Um, so VS Code has great Jupyter Notebook support. So it's what I normally use for doing Jupyter Notebooks. I know there's lots of Jupyter Notebook things. Um, so if you have VS Code installed, I would just use that because it makes it easier for me to help you. But if you have another, and I know it'll work there, I guess. But like if you're using, for example, the web portal for Jupyter Notebooks, I think it doesn't like you to install. Um, Anaconda has betrayed me too many times, so I don't like Anaconda. But again, if you have Anaconda all set up, and if you're comfortable with it, you could just use Anaconda. Um, my university also pulled its Anaconda license, so we're not allowed to use Anaconda. Yeah. So if you have Anaconda, yeah, as long as you can get it working, then anything should be perfect. So VS Code will let you choose whether to use Anaconda or virtual environments or like VMs. Whichever one you want to use, it should work fine for something like this. I'm just sort of going through yeah, Spider should also work. I used to use Spider a lot. Um, The other the other place to get files that's very good is CDDIS. I mean, it is up to you, Mohammed. But I know VS will work, I guess. So, um, if you have VS installed, then you might as well use that because it will look like my screen. Um, if you're really familiar with Anaconda, it should work fine in Anaconda. I put a link to another place there. This is sort of the main repository for GNSS things, but you need to create an account, um, which I figured would be another layer of complexity on top of everything else today. So that's something that you'll probably want to do in your own time, but for right now, you don't need to worry about it. But just if you already happen to have an account, then you're good to go. Has everyone been able to run the setup code? So, like, if I run it, it's just not going to do much because everything should already be installed. Um, yeah, hey, that's a good point. Earth scope is another place. Yeah, doing the pip install of GeoRINEX does take a while. Um, it does. So in the background, it is doing a lot of stuff. It has to install a lot of other packages. Yeah. So, right, if you were able to run that successfully, it should already look like mine. Um, it's going to install a bunch of other things, NumPy, some decompression things, pandas. Um, so this is the reason to make it in a new virtual environment is that if you do everything in Python in one sort of your global Python environment, you can end up with inconsistencies or conflicts between packages, and that's always a nightmare to sort out. Um, so it's always nice to do a fresh project for whenever you're doing a fresh virtual environment for a fresh project, but not necessary necessarily. Um, but then if you do matplotlib, you need this library called bottleneck, and then you need scipy. And then you should be good. So was everyone able to do that? To install what? Oh yeah. So the syntax that I provided doesn't work um, before. So what you have to do uh, is go to here, right? And you click code, and you just have to download the zip file. Or you can do like git clone. Oh, what would it be? Oh, that's not right. Oh no. What did I just do? Okay, no, it's good. So if you just do git clone, uh, git git clone this, it will make a nice little directory right here. I did just test. So yeah, this is what a virtual environment does, right? And this is why I say it's always good to create a new virtual environment, is that it essentially creates like a clean mini Python universe, right? Um, so that whatever you're working on can install the packages that it needs, but not a whole bunch of new ones. So Conda instead of Anaconda, Conda can do this. VEnv can also do this. I find that VEnv tends to screw things up a little bit less. Um, so, right, like in VS Code, I have here, it's using this, right? It's using a little virtual environment that's actually in this directory. It creates VM/script/slash Python. It creates a copy of Python and sticks it in here. And then only the packages I'm using for this project end up in there. So like I could create another one. I could say, right, create Python environment. I get an option between venv and conda. So I could say, I could create a conda one. Let's see what that does. Oh, okay. I don't have conda installed, so I cannot do that. Um, Too many things are trying to happen at the top of the screen, right? So I could select another kernel. I could create a new Python environment, a virtual environment. I could delete and recreate. Yeah, so it's saying you already have a virtual environment here. Why do you want to make a new one? Um, yeah, yeah. So there are some cases like I have a library that I use that requires a very specific version of pandas, right? So if pandas goes above version 2, it just breaks, right? Um, so I need to make sure that it always runs in a specific environment where pandas is always not above version 2. It has to be a version 1 pandas. So the only way to do that is with virtual environments, right? If I didn't, then every time you tried to do something, it would fix, right? You try to fix your Python code for one project, it would break all of your other projects. And it just, yeah, it is fun. Python is great, but it has its quirks. Is anyone still having trouble? For people who do have it up and running, right? So you can start playing around with assignment one. It should be pretty self-explanatory. I often have, right? So it just takes you through how to read in the data, how to just look at what's in the file. Um, yeah. So I guess in the interest of time, I will keep going a little bit, but hopefully the code will be self-explanatory for this first one. It should be pretty easy to self-guide your way through it. Um, so hopefully most of you, I think, will have seen Jupyter notebooks before, right? So you import all of your libraries. Um, which always takes a little bit of time, especially on this computer for me, I find. We will actually load the data in. So all of the data for assignment one is already all downloaded. Um, but just, yeah, I was just showing that mostly for if people already had the notebook up and running, they could just browse through the directory and see what was there. Um, so there's a folder here called data that already has all the data that we need for the examples in it. Um, so here we have, all right, so this is sort of a very old school file. Okay, you weren't able to do. Did you run the setup notebook? So it has some instructions about the virtual environment, but then it does. Did it not work? Okay, if it doesn't work, you can always do. You could always try installing the normal GeoRINEX. If you're having trouble installing it through Git, depending on what program you're doing, you could do pip install uh, GeoRINEX. That will install the normal one. It is fine for version 2, but it's very slow for loading version 3 files. So it'll work for the first example, but the later examples will be slow, we'll say. All right, so you can see it only takes, it took a little less than a second to load the file. And if we just write data here, you know, it looks a little bit weird because I have, dark screen on. Um, but we can see a lot of stuff about it. So, right, if you haven't used Xarray before, Xarray is a really great library that we'll see a lot. So this is a data structure essentially. So we have a bunch of coordinates, right? We have our time, we have our SV stands for, I think, like space vehicle or satellite vehicle. So these are all different GNSS satellites. Then we have our data variables. So we have C1 and P2. These are our ranging codes. Um, and if we look at that, ooh, that's hard to see. There, that might be a little bit better. It's essentially a NumPy array where one of the dimensions is time and the other dimension is satellite vehicle, right? We have similar things for L1, which is our phase for the first carrier frequency, right? L2, P2, right? All of our observables from the RINEX file. And we get some attributes from it too, right? It says it's a version 1 RINEX file, which might actually be true. Um, yeah, the interval is 30 seconds. It's an observation. Um, the time system is GPS. There's the file name. It actually tells you the model of receiver. So this is a Trimble Net R9. And the receiver position, which in this is an ESEF coordinate. So it says that the receiver is in the middle of the Earth at the very core. Yeah. So that's the other lesson that I will tell you is if it's an IGS station, you can trust the position in the file. If it is not an IGS station, do not trust this position. Um, Yeah. They basically have to be entered in by hand. They're not produced automatically. Some person types them in, and people are bad at typing, and or sometimes they don't bother to put anything in at all. So I did a survey of this once. About 10% of RINEX stations have errors greater than 100 kilometers in them. So IGS, yeah, so IGS is um, IGS is the International Geodetic Service. So this is the international consortium that basically handles GNSS things. Um, so they are the people who figure out what, like, where the satellites are, and they do things like, yeah, all kinds of stuff. So they have this nice map here. They have all kinds of these are their reference stations. So yeah, there's all kinds of stuff people do, like trying to figure out like where the Earth's crust is, and like how, where is the Earth, basically. How is the shape of the Earth changing and things like that. These are the reference stations that are used for like figuring out the precise orbits and stuff like that. Uh, so they're the people who run all of that sort of stuff. You can see Africa does not have a lot of these reference stations, which is a problem, right? South America is a lot better than it used to be, but if you look at something like, you know, California, there's loads of them. Um, but this is yeah, the IGS. Yeah, sorry, I should have clarified that. Um, all right, so there's some things that we can know. We can see how many satellites are in the file. This one's GNSS only, so it has 32. Sorry, it's GPS only. All right, it starts at, was that March 22nd, and it ends at, 30 seconds before midnight on that day. We just have our basic GPS observables, and we know a little bit of other information. So now we can plot it, right? So we do plt.plot, right? We can plot all of the nice, you know, phases. Um, yeah, you can see they're in kind of a weird unit, and that's actually just like a count. It's just counting how many phases go by. Um, yeah, if we just copy and paste this, yeah, I tried to do, pedagogy by making you guys type it all out, but I'm going to be lazy and just copy and paste it. Um, if we want to look at the pseudo ranges, you can see, here, this is, what did I do? What for C1? So this is the C1 pseudo range. So the L1 carrier frequency, and this is the coarse civilian code, and then this is the our attempt at decoding the precise military code, which is kind of fun. Um, the nice thing about X-array is it does a whole bunch of the reason why it's so powerful is it does all the indexing and everything for you. Like, right, if you want to take the difference between P2 and C1, it knows P2 and C1 are aligned in time and satellite vehicle, right? So you don't need to worry about the shapes of them and things. Like it knows, okay, you're asking me to subtract them. Well, clearly you mean like this time and this time should be subtracted, right? So you can just take the difference between them, right? So, you know, this is just showing the difference between two different ranging codes. And if you know about where tech is calculated, this is actually tech right here, mostly, right? These curves that we're seeing, these sort of characteristic arcs, are because the angle is changing. So as you get to lower and lower elevation, you go through more of the ionosphere. Um, but this is essentially a tech calculation. Um, you can do other stuff. There's just lots of examples of using X-array. So if you want to take a mean. There's a few different ways you can do something like that. You can throw these things into NumPy functions, and they will, right? You can take a mean of something. Um, there's another one here. If you'd want to do like a rolling average, right? So this is sort of trying to smooth those arcs from before. Right? If you scroll up and compare them, yeah, right. So it's a really powerful library for doing lots of data analysis kinds of things. Um, you can also do derivatives if you want. So how are we doing for time? We're doing okay. Um, so here we have, so this is, has everyone had a chance to kind of play around, I guess, following along with what I've been doing? I tried to set it up as a bit of a skeleton so that like when you are doing your own projects and things, somehow, yeah, fair enough. When you're doing your own projects, you'll have these sort of code examples that if you need to take a derivative of something or you need to smooth something, you can just sort of copy and paste these functions and look up how they work. And Xarray is really well documented, but they're the kind of things that tend to be useful. Um, so here we have another example. This is a more modern file. Um, so takes a little bit longer to load, right? 2.1 seconds. But now we can see, now we have 479 times. We have 67 satellite vehicles now, right? So if we look here, we can see we have these C's, E's, G's, and R's. So E is Galileo, G is GPS, R is GLONASS. I believe C is Baidu. So we have a whole mix of sort of things here. You can see we have way more data variables than we had before, right? So in version 3, we don't just have those simpler codes, right? We have more complicated ones. So they tell you the first one, all of the codes in version 3 start with a C, and then so the first letter C is for code, D is for Doppler. I know this is hard to see. C is for code, D is for Doppler, L is for phase, and S is for signal strength. Um, and then the number afterwards tells you which carrier it is. So if it's a 1, it's L1, 2 is L2, 5 is L5. But then we get other ones, right? There's 6, there's 7, there's 8, right? Those get used by Galileo and things like that. So we have 4 or 5 different carrier frequencies through this file. And then you can see some of them end with C's, L's, P's, I's, S's, W's. All right. There's a link in the PDF, the presentation, to document all of these things. Um, but yeah, so right, we saw in that table, there were a whole bunch of different codes. These are all of those different codes, right? The military codes, the civil codes, the search and rescue codes. There's all kinds of stuff in there. So this is what a modern GNSS file looks like. And I know it's a bit overwhelming. Um, right, and then there's other things, we can see it's a version 3. It has the file name here. I trust this position because this is a pretty good station, right? This is one that's in Uganda. So if you want to check the position of something, there are services. I used the other day just what is it called? This works. This works best if you only have a small number of stations to do. But if you have a station that you really care about and you really need to know where it is, these people will let you upload a RINEX file, and they will do all of the nice geodesy and calculations for you. And they'll give you a really nice, they'll email you a document with where it was and everything else, and it works great. Um, yeah, it's free. If you try to do 10,000 stations, they might get mad at you. But it is free. It's just a nice service. So, most of these stations don't move around very often. So if you have a small number of them that you need to do, or something looks suspicious and you want to check it, something like this is great. And lots of countries have these. Canada has one too. I just used the Australian one for this tutorial actually to find the position of a station. So yeah. So here, this is an example of going over a loop. Right, I'm saying, okay, right, Xarray has lots of good tools for selecting data. So I say select this. Um, I said I'm not familiar with that software, so I can't really comment on it. Um, yeah. Yes, what was I doing? Right, so you can select some data, you can go through, you can loop over things. Right, so this is checking for this one if it actually has data or not, basically. So I'm saying only get the data that corresponds to this satellite, right? So if we do that, right, what does that look like? So now we've lost a dimension, right? There's no satellite vehicle anymore. It's just a certain time, and it's just a bunch of data variables, but this is the subset of the data for that one satellite, right? And for example, I just had it print over and say, is it all nans? If it's a nan, say it has no data. So you can see, right, these ones are the GPS codes. We have data for that. We don't have data for any of these ones. These ones we do have data again. Right, so you can kind of pick out just which ones we actually have data. And then I just plotted all of the data that's there for this one satellite. And you can make a whole bunch of plots really easily. Um, you can say select only those ones that have GPS data. So here I said, give me a list of all the GPSs, right? Give me the subset of the data for GPSs. Find all of the observations that actually have data and get rid of everything, right? And so then we just are left with something we have, right? This file is only for a partial bit of a day. Something went wrong with the receiver. So we end up with just a smaller, more manageable subset that only corresponds to GPS. So nice, easy. Yeah, sorry. I had originally designed this to be a much longer lecture, so I am rushing a little bit. I'm sorry. Uh, yeah. So the assignments are here, and you'll be able to work through them in your own at your own pace. I tried to write them so that we have an idea of what's there. So I might switch back to the lecture now, but you guys should be able to work through the um, the data, these files just to be able to. It's just to give you code snippets that'll be useful, hopefully. So I won't worry too much about that because we actually haven't even talked about tech yet. So let's switch back to tech, and then we can switch back to code in a little bit. So yeah, we've been talking about it, and I'm assuming a lot of you probably know what tech is. But right, what it is essentially an integrated measure of how much plasma there is between the receiver and the satellite. So if you just take, you know, a column of plasma and you integrated it. You integrated along that line. That's just what the tech is. Um, and the reason we can get that is that plasma is dispersive, and the electron density affects how long it takes that time signal to propagate. So this is a really fun slide, right? So there are all kinds of things that affect the propagation time. And this is just sort of a list of all of them, right? You have the geometric range. You need to care about the speed of light. You have to care about the errors in the clocks. Um, the troposphere, the neutral atmosphere, has a delay. That depends on humidity and all kinds of stuff. The ionosphere causes a delay. The receiver hardware causes a delay. The satellite hardware causes a delay. Multipath produces errors, and then the receiver has noise from the correlation and things that also cause errors. So what you measure with that pseudo range in that file is the sum of all of these terms. But I've highlighted some of them in red. So these are the ones that change depending on your carrier frequency. So the geometric range doesn't matter what carrier frequency you're on. Like the physical distance is the same either way. The clock errors doesn't matter. The tropospheric delay doesn't depend on frequency. But these other ones do. But this is really powerful, right? Is that we can combine two different frequencies to get rid of non-dispersive effects, right? So we can get rid of all of the terms that don't have anything to do with frequency. So we can cross out, right? If we take one pseudo range and another pseudo range and we cross them all out and we do some algebra and rearrange, you essentially get this term at the end. So you get a term that's proportional to the slant tech. You get a term that is a hardware dependent, so it's called this a differential code bias. So it's a hardware term that depends on the receiver, a hardware term that depends on the satellite, and an error. And this proportionality constant just depends on the frequencies. And that's it, right? That's why in the Jupyter notebook, when I took the difference between the two pseudo ranges, and I said, this is basically a tech measurement. It's because it is, right? The dominant term here is the ionospheric term, right? You get rid of all the pesky positioning and timing, and you're just left with the ionosphere. The reason why GPS and all these other ones have at least two frequencies is so that they can do the opposite, right? They want to get rid of the ionospheric term by having two frequencies, but we do the other way around. We get rid of all of the position information to preserve the ionosphere, right? So we see here is a one pseudo range, here's another pseudo range, and then here's the difference. Boom, right? So they look identical basically, but once we change the measurement, the difference between these two signals, right? You're going thousands of kilometers. The difference between them ends up being something on the scale of a few tens of meters, right? And this difference of meters is what our slant tech measurement is. This is how we get information about the ionosphere. But again, it's very noisy, right? It's shaking around, it's doing all this stuff. So we can do something very similar, and I won't belabor this too much, but with the carrier frequency. And the one thing that's different, really, is that there's this integer ambiguity in the phase, is that you just have a random arbitrary number added to this, right? But you can go through everything again, and it looks a little bit more complicated, but we can basically say, okay, we have another term that depends on the slant tech, and we have this large arbitrary offset that we don't really care what it is, but we know that it's there, and we have error. So now we have two different ways of measuring tech, right? And so here's a nice example. So we have this noisy one, which comes from the pseudo range or the code. And then we have this nice smooth one, which comes from the phase. But you can see the phase ones are sort of random, and they often have these big jumps in them. So what these smooth ones are, right? Every continuous set of phase measurements we call like an arc, a phase arc. So we need to identify them, right? We need to say, here's a continuous arc, here's a continuous arc, here's a continuous arc. And then we need to level them to the code data, right? Because these should be the same, right? They're the same ionospheric signal, but one is noisy and the other one is smooth. So this is what gets called phase leveling. where basically we take all of them, we say, okay, this one needs to go down by 90 tech units. This one needs to go down by 26. This one goes up by 36. This one goes up by 35. And then boom, you have a nice smooth tech instead of that very noisy one. All right. And then if you just take all of the data that you get and you can smooth them all out, it's really nice. We won't worry about this too much, but this is just just showing that the different signals have different amounts of noise, right? So you can see L5 for GPS is the least noisy, L1 is kind of in the middle, and L2 is quite noisy. Um, and you can see in individual arcs, it's very noisy at the edges, and then it gets smoother right here. You can see it's lots of noise, smoother, and then lots of noise. This is that multipath again. So people often say, oh, get rid of data that's within 15 degrees of the horizon and stuff like that. Um, but basically, that's how you calculate tech. It's very we'll work through it. We'll go back to the notebook and look at the second example. Yeah, so code comes from the so this is that pseudo range code, right? It's a pseudo random number that's getting correlated in the receiver that has the time signal kind of encoded in it. So that's how we figure out, yeah. So that's the code, and then the phase is the phase of the carrier signal. So overcoming the integer ambiguity, that is what assignment two is all about. So if we open up assignment two and import everything again, right, you can tell we're going to do real calculation because we have the speed of light and some frequencies defined now. And we're going to use that same first station because it's just nice. It's simpler to use GPS uh, than the other one. So if we plot things, right? All right. So has everyone made it as far as here? So what I'm trying to plot here is the phase and the carrier for number one, the first frequency, and the phase and carrier for number two. And you can see that they don't really agree with each other, right? And that is because they are in different units, essentially, right? So the pseudo range is in either seconds or meters. I actually don't entirely remember. Um, and the phase is a count of how many phases. So we need to correct it. And I kind of breezed over this in the slides, but it is in the slides. We need to correct it with the wavelength. So if we do that, which we can do here, right, then if we run the plot again, you'll see that they basically look identical now. The phase and the carrier look on the scale of, right, so this is a measure of distance, right? We're talking, 10 to the 7 meters. Um, all of these effects that we're talking about are, you know, fractions of meters, maybe tens of meters that are happening on a time scale of, something on the ground and a satellite out in space, which is, you know, they're at what, 20,000 kilometers in altitude. So they're roughly 20,000 kilometers away. So these are tiny, tiny, tiny changes in the overall signal. That's what we're pulling everything out of. Um, so basically, just to say, this is a really common mistake that people make is they forget to correct. Right? You get the phase in the file, the RINEX file. You have to divide it by the frequency for the carrier to convert it to the right units. But, we say here, now that we have done this, these are essentially, right, what we're plotting here is the L1 minus the L2 for carrier, and for the code, it's 2 minus 1. That is also in the slides. Again, I breezed over it, but the signs are different. So for right, it's 1 minus 2 for the phase, 2 minus 1 for the code. If you want to follow the math, it'll be in the PDF. But basically, this is two different things, right? So we have here, these are down here is the tech that we get from the code. And here are all of the arcs of tech that we get from the phase. And you can see this file is actually really nice. It has very few cycle slips in it. And I found it completely by accident. Um, but you can see that there's all this sort of arbitrary spread, right? They have the same shape, but they're much smoother, but they're just kind of all over the place. And this is exactly what Sarab, if hopefully I'm saying that right, said is the integer ambiguity, right? There is some ambiguity between, and in tech, it actually isn't technically an integer. So there are other terms like phase wind up and all of these other things that are fractional. So we don't expect the correct answer to be an integer necessarily. But that integer ambiguity is the biggest part of it. Um, so what we can do is, right, this isn't exactly tech yet. This is in um, either nanoseconds or meters. I forget. Um, but we can just calculate that proportionality factor, right? So the frequency 2, frequency 1, this magical 40.3 number. And then we can calculate, right? We can use X-array to do all this indexing and stuff for us, but the phase tech and the code tech are right there. And it's easy enough to plot them. Boom. So now they're in the right units, which you can see, apparently there is, hundreds of tech units here. But this is partially the biases, which we'll get into a bit later. But now these are both in tech units, which is nice. So what I'm doing here is I'm going to say, okay, let's do some phase leveling, and it'll make a bunch of nice plots. So basically what I'm saying, this is just some other stuff for doing that, is, all right, I'm going to do a difference between the code tech, the phase tech, and I'm going to select specifically just one satellite at a time, right? So I'm looping over all the satellites. I'm going to say select just one satellite, and then I'm going to do a little plot, right? And I'm going to plot the code tech, the phase tech, and then the phase tech plus this arc difference that I came up with, right? And we'll see how that works. So you can see here, the blue is the code, the orange was the phase, and the little green line, if you can see that with the compression, um, just goes right over top of it, right? Code, phase, level, it all works more or less perfectly, right? At least whenever there's only one arc. So you can see the integer ambiguity is, it depends on what arc number you're at, right? So here, where we have three different arcs, that integer ambiguity is totally different for all of them. So we need to have some way of identifying phase arcs, right? This is why it gets hard, right? Just taking a mean between the two of them is fine. It's detecting the cycle slips and the breaks in phase that's the problem. Um, but otherwise, this is all it is. This is tech processing, right? You open the file, you subtract a couple of things, you divide by a frequency, and then you just calculate the difference between them, and you're basically good to go, right? If it wasn't for cycle slips, it would be very easy. Um, so we won't worry about this too much. So there's a function in here called GNSS tools that has a bunch of little helper functions in it. It has something to read in those navigation files and convert them into like orbital positions, which is really nice. It has some basic code for phase leveling, and it has some code here for finding elevation angles. So if you need to do elevation cuts, we can do that too. But essentially, what this is a bunch of steps. So basically, we look for things that we think will cause a break in the arc. So if the whole RINEX file is missing data, we can say, okay, right? We'll treat that like a cycle slip. Um, if there's a nan data, not a number, then that means either the satellite is not visible or something else went wrong. That's a break in an arc. If the derivative is too large, right, that means that there might be a cycle slip. So we'll say, boom, we'll pick that. If the jump from one time step to another is too large, that could also be a cycle slip. So we'll say, all right, we'll flag all of those. And if any data met any of those things, we're going to say that is probably the edge of a valid arc. And then there's just a bunch of stuff to essentially find all of the start and end points. And then we go through all of the arcs and do essentially the same thing that we just did, where we just find the mean difference between the phase and the code and adjust the phase. And if we do all of that, get a bunch of plots, but that will look very nice this time. So the one thing that's about all of this is that when Mahith shows you where you can go and just download a bunch of VTech data that's already been done for you, you'll go, oh, why didn't we just do this the whole time? And the answer is it's not perfect. It has problems in it sometimes. And so, right? And it won't help you if you have a GNSS receiver on the roof of your university that you need to try and do a tech study with. Um, but that's okay. So we're just going to wait for the notebook to catch up now. Right. So now we have all of these nice arcs, right? You can see the blue, you get this sort of wild shape and this nice clean black line on top of it. And then that's it. That is properly phase leveled code. So it's all broken up here so that you can understand all of the steps and work through them. And you can plot the things, you can see where it's flagging stuff if you're interested in really seeing how it works. But it's a really simple piece of code that should just do this phase leveling for you. And you can see right now we can see lots of nice little structures in here. This might be a TID or something going by. Um, Actually, it looks like there's quite a lot of that going on, right? You have these waves over the course of hours. Um, so the hard part is always knowing how much of that is real and how much of that isn't, right? You can see here in the code, it kind of looks like there's a TID, but we don't see that in the phase data, right? Um, so that's why it's important to be able to smooth it. And yeah, now we have, everything is leveled nice and properly. But you can see the phase leveling code, it's nice and it's very quick, right? It takes on my computer, just a laptop, 0.2 seconds to do that phase leveling. Um, so yeah. Has everyone had a chance to sort of play around with it a little bit? I know I'm rushing through pretty quickly. Yeah, that's good. Right. You can see it's still not, probably perfect, right? So you can see in the end of the arc at the 10th satellite, it gets a little bit wonky there. Um, so this is why the elevation cuts become so important, is that the multipath errors are just too much there. It's trying to level things and it's just not going to work. So, yeah. So the nice thing is like, right, for the sake of your project, if you are just doing this and you never want to think about it again, right, you can say, all right, I will I don't care about this. It's just, um, yeah. Actually, maybe a good example for us to work through would be to do an elevation cut, right? So if I scroll up way at the top, right, I have the station coordinates. I just had to remember what I called that variable. All right, so in the bottom of number one, I so in assignment one, I kind of skipped over it, but we can talk about it now. So I talked about RINEX navigation data. So we can see here it has a bunch of data variables. They're very different from the ones we saw before, but if you're familiar with orbits, yeah, the recording will be available and the slides will be available. Um, and I have some papers listed that go through some of these things too. Um, so, all right, you can see there's a whole bunch of stuff in here that if you are familiar with orbital mechanics probably makes some sense, right? Eccentricity and omega zeros and all this other stuff. But that's really hard to work with. So there's another function in here called um, nav to orbit that I wrote up that basically take all of that information, all of those orbital parameters, and convert it into a nice, friendly array that has all of the satellite positions in it. All right, so it converts it into an X, a Y, and a Z. These are in Earth-centered, Earth-fixed coordinates. Um, and that's really nice. Because if you want to, you can then do things like plotting, in three-dimensional space. That's where all the satellites are, right? Um, so the reason why this is useful is that if you want to, say, do an elevation cut, this is exactly what you need. So we'll come over here, we'll load that in here. We will grab the orbit. Perfect. Just need to wait for that bar to go away. Okay, apparently it's never going to go away now. All right. So the nice thing about it, right? So this orbit is one X-array data structure, right? And we have this other one that we got from our function called data, which is our slant tech data. It is another function, right? But we have one dimension here called time. We have another one called time. And it's smart enough to know that they're both times, they're both date times. You know, you can do stuff with those things together, right? You could do data. I think this should work, right? This doesn't really make sense, but it's smart enough to know what you're doing, right? It can figure out the slant tech and the orbit are both dimensioned the same, so it can add them together even though they're in different structures. Which means if we do something like GNSS tools, and we'll do elevation. So this wants all of the receiver positions. Did I call it station chords? Yes. Uh, so this software that's GNSS tools is just a Python function that's in the work the Git repo that we're using. So you can just import it as a just because it's a piece of Python code essentially, and it has these functions in it already. Um, they're basically I copied and pasted and in some cases simplified um, some functions that I use to run my models, um, and just said, yeah, like this is the code that I use for calculating like my ionospheric data assimilation models. So I just cleaned it up a little bit and put it in here so that you guys can use it. Uh, So if you find any bugs, let me know. That's helpful, right? So this is calculating the elevation angle. I think in radians. So if we do, all right, this will calculate for us elevation angles. So we could do this. We could say data. So now our data structure here that we have, right? Before it just had STEC and STEC error in this arc index, right? But now it has our elevation data. But you see, it's not terribly exciting. Um, Also only ran for 50 minutes. Why did it only run for 50 minutes? Hmm. You know what? As soon as I said, tell me if you find any bugs, I immediately found a bug, apparently. Um, yeah, so the elevation angle is just the angle that the satellite appears to be. So from wherever you are on the ground, right? The elevation is essentially how many degrees angle between the horizon and the satellite. So it's what you want to know how close a satellite is to the horizon, essentially. Um, yeah. I'm not sure why this is only giving me a plot for 50 minutes of data, but I will have to investigate that. There's always a problem with doing a bit of untested stuff. Uh, so I will just quickly, assignment three is less complete, but it is, all right. So the other problem, right? If we go back to, really wish this bar would disappear from the top. It's kind of hard to, I don't know if you guys can see it because it's part of Zoom, but it's blocking all of my tabs. Um, Here, we'll go. So if you open assignment three, I also included some code here for reading. So this is the link to where you can download this. You can get this from CEDAS. But there are these files called RINEX files that contain information about receiver biases in them. So if we just just do all the tech calculations here. This is all the same stuff from before, but with a different file. Right. So this is ABMF. Um, right. It's one of the IGS stations. So if you do the tech calculation, you get something that looks like this. Right. Um, Yeah, you can see this one has a lot more, breaks in the arcs and things like that, but that's just it's just a noisier receiver. Um, so you may notice some strange things here. So this is in tech units on the y-axis, right? And we have negative tech units, right? If tech is an integrated quantity, it always has to be in real life greater than zero, right? Like you can't have negative total electron content. Sometimes you can measure negative total electron content, and we'll talk about that, but it can't physically be negative, right? If you have no plasma, tech is zero. You can't have unplasma. So what this is because of those hardware dependent factors, the DCBs, which are sort of the nightmare of anything to do with tech. Sorting out what your DCBs are is difficult. So the reason why it happens is, you have an antenna and you have a receiver, and the antenna, uh, your radio wave has to enter in the antenna and go through the cabling and go through the receiver, and it's hitting interfaces of materials, and there are transmission line effects and all these other things. The end result is that your code for different carrier frequencies takes slightly different amounts of time to travel through those wires and circuits and things. And so that means that you end up with this static offset, right? It looks like the ionosphere, right? It's a difference between the two frequencies, or a difference between the two codes, but it is not from the ionosphere. It's from these hardware effects. But the nice thing about them is that they change very slowly compared to the ionosphere. Um, and in the case of the satellites have them, the receivers have them. Uh, so what you see here is this is uncorrected data, right? You can see that there is a span, right? All of these things at nighttime, right, are measuring, what is this, like a 30 tech unit difference between all of the different satellites, which is doesn't make sense for nighttime, right? And you can see a bunch of this is negative, right? That also doesn't make any sense. And so this is the DCBs. So what the SINEX file lets you do, we'll just check ABMF is in the data for the SINEX file because this is an official IGS station. So we can say select the subset of the data that corresponds to that satellite. And if we take a look at it, we can see here we have a whole list of all kinds of combinations, right, in this file. And we can see, our station DCB, we don't have all of them, but we have a whole bunch of them, right? These are all of the biases that the IGS, I know that's going to be hard to see. These are biases that the IGS has determined for us. And specifically, this is from the Chinese Academy of Sciences. Right, they're one of the IGS stations, but this CAS at the beginning, right, means it's from them. For example, so in RINEX version 3, this is the equivalent of our basic GPS combination, C1C, C2W, right? So we can see if we just pick that, our station DCB, it is 38 tech units, right? And so if we go here, right, you can imagine if you add 38 tech units to all of these, they will all be positive at the very least, right? Um, so that's a good sign, right? And so what you can do is you can say, okay, well, I'll just take that data. What does it look like if I do that? Right? You can see, boop, we bump everything up. Now, that we've sorted out the receiver bias, everything is positive now. But of course, there's also satellite biases, which the SINEX file also has. So what you can see if you do that is that everything gets much tighter, right? You can see now at nighttime, there's very little spread between all the different arcs. Right? And that makes sense, right? At nighttime, you don't expect to see a lot of tech. You don't expect to see a lot of differences in tech. And so all of your arcs should be very, very close together, even in slant tech. VTech is even more so, and Mahith will talk about that shortly. Um, but yeah, so and if you do both of them at the same time, you can see here that it's still negative. But if you do both of them at the same time, right, this is what you would get for tech after correcting all of the biases. So you can see nothing is negative. You have your nice nighttime tech here. There's a couple arcs that are a little bit wonky, but such is life. unfortunately. Uh, and then you can see that you have during the day, depending on what specific slant tech you have, what look angle you're at, you can get these sort of wildly different looks. Um, but generally, this is sort of the pattern that you expect to see. And this looks a little bit weird. So a bunch of links. So this talks about, right? So what do you do if you have a station that is not an IGS station, if it's not in these SINEX files? So one thing that you can do is you can download a GIM, a tech map, right? And this is essentially a map of the ionosphere that someone has made that you can use as a reference, right? And I meant to put it into the talk, but um, yeah. Right. So you can say, okay, well, the reference says that my text should look like this roughly. And so I will level I will try and figure out what my bias is based on that. And I put some citations here to some work that talks about that a little bit. Another one that works really well that you don't need a tech map for is something called minimization of standard deviation. And you can get that in this paper here. And essentially what you're doing, it doesn't require any external library. You do need to correct the satellite biases, but the satellite biases you can always get from the SINEX file. And it looks a little bit wonky, but essentially you just try a receiver bias and you just try a whole bunch of them. And then you calculate the standard deviation of your VTech that you get at the end. And at some point, you will reach a minimum, right? There is some choice of receiver bias that gives you the smallest variation in VTech. And you just say, that's my bias. And it works pretty well. You do need a whole day of data for it to be reliable, but it does work pretty well. It will give you something that is basically right. So if you just need to get a bias that's good enough, um, minimization of standard deviation works really well. And I have a bit of code that can do that with these formats. I just haven't had time to put it in. So um, I can add that to the repo and update it, and then you could download an updated version. But it isn't. It's a nice exercise, I guess, to implement it. It's really not too hard, right? You just take this, you calculate the elevation, you do the VTech stuff. But Mahith will show you that in practice, right? If you aren't concerned with doing this for your own individual station, right? There are products where people have done the VTech calculation and things for you. And it does make it a lot easier, but the caveat is, depending on the kind of study you want to do, it's important to know how to do one or the other. But I know that was a lot. It was a bit of a whirlwind, but it's a pretty complicated topic to try and fit into 2 hours. So I guess before I hand it over to Mahith, does anyone have any questions? I mean, I'm sure you have lots, but yeah, I'll update the code. I'll figure out what's wrong with the elevation calculation. And then I'll add the minimization of standard deviation because that's just a nice tool. Yeah, yeah, you can always ask me. I'll put my email in here too. So you can always email me a question if you can't get a hold of me some other way. Um, yes, so those are both very fair questions. So so this is true actually. So anything involving VTech um, is essentially assuming that there are no horizontal gradients. Um, so when you are at low latitude regions and you're in the equatorial ionization, that assumption just isn't valid. And so any work involving VTech at low latitudes, you have to be very, very careful. And so even choosing how you handle like elevation cutoffs becomes really important because the lower in elevation you go, the more data you have, but the stronger the effects from those gradients become. There are ways around it. So uh, there are DCB estimation techniques that do not rely on any um, horizontal homogeneity assumptions, but they are pretty complicated. Um, so yeah, um, I have a paper on doing it for my data assimilation models, but that's sort of out of scope of this. Step one is have a three-dimensional data assimilation model. Um, but if you're interested, it's probably a good read. Um, yeah, it definitely has an effect. But the I guess one advantage of being at low latitudes is that because the ionospheric tech is so high, right, a 5 tech unit error in DCB at high latitudes is a disaster, right? That is an entire 100% error in your ionosphere, right? A 5 tech unit error at low latitudes is a 5% error, right? So the relative importance of the errors also does change depending on where you are. Um, but yeah, there's one of the challenge. Yeah, there's a lot. I could talk about that for ages. Um, yeah, I think if you want to see, yeah, this is my paper of I didn't trust anyone's biases for high latitudes, so that I did it myself. Um, yeah. So this actually has the um, and actually genuinely this will be helpful too because the even if people don't want to look at this, the references in this, like I do give a bit of a discussion about like DCBs and things in this. Um, so here, for example, you can see this is one station, and this is a good example of describing how it works if you're using an Ionix map. So all that you can see here in gray, these are the slant tech arcs. And if you map them down to VTech, you get something that looks like one of these curves here. Right? So you're taking all the geometric information out and you're mapping it down. And so you can see here, uh, right? So the purple line is Madrigal, which I think Mahith will talk about. The blue line ends up being what you would get more or less from one of the dashed line is what you would get from like an Ionix GIM, a tech map. And so essentially what you're saying is you take all of these, you map them down to something, and you just level it again to what the Ionix tech map is saying. And that's how you figure out the DCB. Um, but what I did for mine is if you really like math, there's a whole bunch of math here of how you can do it without assuming um, a VTech structure. And then this was essentially comparing it to the VTech things. And then, yeah, it's a bit of a wild paper, but it is there. The important thing is it talks about here in the introduction. Yeah, so like how you map from VTech to or slant tech to VTech and how you would find a DCB. So, um, yeah, so the reason why the elevation angle is important is that that's what you need. to convert to VTEC, essentially. So you need to know where the satellite is to know what the elevation is. And then once you have the elevation, you can then convert to vertical tech, which destroys some information but makes it very helpful for some things that Mihith will talk about. Um, so a good example, actually, I'll go back. Um, sorry, I'm going to end up clobbering what Mihith is doing a little bit, maybe. Let's see if I can find this here. Oh, wait, this isn't the one I want. Hmm. All right, I can't find the paper. There we go. So if you wanted to, so this is an example of like we had in New Brunswick a series of GNSS stations that again, like they're not IGS stations, you know, you got to do all the bias stuff and everything. Um, but right, so we had a small set of stations here, and this was for looking at the solar eclipse. Um, I'll put this in here because this is probably a very good explanation of a lot of what I've covered here, but worded a little better, maybe we'll say. So again, you can see, you know, we have a whole bunch of slant tech arcs, and then if you convert it to VTech, boom, you get something like this, right? And then, so here you can see, you know, for all of these stations, all of the VTech that they get is basically the same. So this is the day before the eclipse, this is the day of the eclipse, and then this is the day after. So if you're one of the eclipse teams or doing a storm or something like this is why it's really useful, right? You can really focus on one specific area. Um, so the reason why you need the elevation angle is to go from this to this. But Mihith will talk about that a bit more. Um, but this is probably a helpful paper for people to look at, right? Again, they're sort of looking at the big storm in May as well. Um, so you can see here is the DST, here's tech, and just anyway, that was pretty wild. Um, any more questions quickly before I'll hand it off? No? And if not, my email is in the chat. You can always send me an email, and I'll get back to you. But I guess yeah, I'll call it there, and I'll hand it off to Mahith.
Thanks, Ben. Is somebody here, or are we taking a break?
Hello, Mahit. Can you hear me?
Yeah, I can hear you.
Hello, Mahit.
I can hear you. I can hear you. Can you hear me? I can hear you well.